Isentropic pressure and density relation. Note that the relations as stated before for the temperature and the velocity, the speed of sound velocity, which was for t, we have and t0 on t, the root of so note that this equation requires only adiabatic flow and hold even the process of irreversibility such as frictionless or shock phase. Adiabatic flows and hold even in the presence of irreversibility such as frictionless or shock phase. Anyway, if the flow is also isentropic, excuse me, let me, if the flow is isentropic, we have adiabatic and isentropic. Then a perfect gas, the pressure and the density ratio can be computed. We have this previous relation for pressure and temperature for an isentropic, which was S1 equals to S2. We had the relation and equals to is for temperature. We had this so with replacing we can obtain the pressure and for the density we can also obtain a relation for rho with eliminating these two k from the relation we can obtain for the density. This relation also can be plotted, and previous pictures have the plotted diagrams related to pressure and density. It is for relation to Bernoullis equations, the next subsection. The isentropic assumptions are effective, but are they realistic? Answer yes. To see why, take the differential equations adiabatic as this meanwhile with in the isentropic process we have so we can obtain this relation for dh, not substituting to this relation we have for the Bernoulli equation. The next subsection is critical values at the sonic point. The signature values and rho 0 at Mach sonic point, which is Mach equals to 1. We have critical properties which are P star, rho star, T star and A0 A star. For P star we have we can substitute into previous relations. For example, we have this relation for T at critical point where Mach equals to 0. We can write T star, for example, on P or T at the selection point. Let me write T for Mach equals to 1. So T on T0 for the critical point. We can obtain also the same relation for A star on A, which was T on T, root of the division of temperature, P star or P stagnation point. And rho star, oh excuse me, rho star on stagnation for the critical points. If we substitute it with the k equals to, we can compute this relation for air, for example. In all isentropic flows, all critical properties are constant. In adiabatic non-isentropic flow, A star and T star are constant. So in adiabatic non-isentropic flow, A star and T star are constant, but P star and rho star may vary. The critical velocity V star equals to the sonic sound at speed A0. We can obtain V star at critical velocity equals to the, because Mach is equals to 1, and we have this relation for the speed of sound. Substituting with the T star from the above relation here, we can obtain this relation for the velocity, critical velocity, which is per second. Some useful relation for air. For air we have isentropic constant is 1.4, so now we can have the simplify the previous relation as these expressions. If we are given the properties, it is equally easy to solve for the Mach number. Minus 1 for the Mach number at a relation to the density, pressure, and temperature. The next section in this chapter is isentropic flow with area change.